When determining the appropriate amperage for subpanel feeding both heat strips and a heat pump, several factors must be considered to ensure safe and reliable operation. The primary concern is the combined load of both appliances, accounting for potential simultaneous operation and adhering to electrical codes. The question at hand involves 10 kilowatts of heat strips within a furnace and a 3-ton heat pump, and whether a 90 amp feed to a subpanel is necessary, given the apparent overlap in their operation. Based on the information presented, a 90 amp feed to the subpanel is indeed required. To understand why, let's break down the calculations and reasoning. Firstly, determine the current draw of each appliance individually. The heat strips are rated at 10 kilowatts. To convert this power rating into amps, use the formula amps equals power divided by voltage. Assuming a standard 240 volt supply, the heat strips will draw approximately 41.67 amps, calculated as 10,000 watts divided by 240 volts. Secondly, calculate the current draw of the heat pump. Although the heat pump's power consumption can vary depending on its efficiency and operating conditions, a 3-ton heat pump typically requires around 30 amps for its compressor and other components. Now consider the potential for simultaneous operation. Although it may seem counterintuitive to wire the appliances for a combined load if they appear unlikely to run concurrently, electrical codes and safety standards mandate that the electrical system must be able to handle the maximum potential load. This requirement ensures that the circuit breaker will trip before any overloading occurs, preventing potential hazards such as overheating and fire. Now, to clarify, the NIC, or National Electrical Code, provides guidelines on calculating electrical loads for various applications. These guidelines are designed to ensure safety and prevent electrical hazards. When dealing with heating and cooling equipment, the NEC requires that the electrical system be capable of handling the combined load of all connected devices, even if they are not expected to operate simultaneously. So, let's delve a little deeper into why a 60 amp feed to the subpanel may not be sufficient. If the heat strips and the heat pump were to operate simultaneously, the combined current draw would be approximately 71.67 amps, calculated as 41.67 amps for the heat strips plus 30 amps for the heat pump. This value already exceeds the capacity of a 60 amp circuit breaker, which would trip under such conditions, interrupting power to both appliances. Moreover, electrical codes typically require a safety factor to be added to the calculated load to account for potential variations in voltage, appliance efficiency, and other factors. A common safety factor is 125% of the continuous load, which means that the circuit breaker must be rated for at least 125% of the expected continuous current draw. In this case, applying the 125% safety factor to the combined load of 71.67 amps yields approximately 89.59 amps, calculated as 71.67 amps multiplied by 1.25. Therefore, a 90 amp circuit breaker is the appropriate choice to ensure safe and reliable operation of the heat strips and the heat pump. So, to recap, the 10 kilowatts heat strips will draw approximately 41.67 amps, and the 3-ton heat pump will draw approximately 30 amps. Adding these two values together gives you a total current draw of 71.67 amps. Then, applying a 125% safety factor to this value gives you 89.59 amps, which is why a 90 amp circuit breaker is needed. In summary, while it may seem unnecessary to wire the appliances for such a large load size given the potential to not operate simultaneously, electrical codes and safety standards mandate that the electrical system must be able to handle the maximum potential load. In this case, a 90 amp feed to the subpanel is required to safely power the heat strips and the heat pump. Also, remember that these calculations are based on certain assumptions about the voltage and efficiency of the appliances. It is always recommended to consult with a qualified electrician to verify these assumptions and ensure that the electrical system is properly sized for the intended application. Additionally, it's worth noting that some heat pumps are equipped with auxiliary heat, which can supplement the heat pump's heating capacity during periods of high demand. This auxiliary heat is typically provided by electric resistance heaters, which can draw a significant amount of current. If the heat pump in question is equipped with auxiliary heat, the current draw of the auxiliary heat must also be considered when calculating the total load in the subpanel. For example, if the heat pump has 5 kilowatts of auxiliary heat, this would add an additional 20.83 amps to the total load, calculated as 5,000 watts divided by 240 volts. In this case, the total current draw of the heat strips, heat pump, and auxiliary heat would be approximately 92.5 amps, calculated as 41.67 amps plus 30 amps plus 20.83 amps. Applying the 125% safety factor to this value yields approximately 115.63 amps, which would require a 120 amp circuit breaker. Therefore, it is essential to consider the potential for auxiliary heat when calculating the total load in the subpanel. Also, it is important to note that the size of the subpanel itself must also be adequate to handle the total load. The subpanel should have enough circuit breaker slots to accommodate all of the circuits that will be connected to it, and the main breaker in the subpanel should be rated for at least the same amperage as the feeder circuit that supplies power to the subpanel. In addition to the amperage of the circuit breakers, the size of the wires used to connect the subpanel to the main electrical panel must also be adequate to handle the total load. The NEC provides guidelines on wire sizing based on the amperage of the circuit and the type of wire being used. It is essential to follow these guidelines to ensure that the wires are not overloaded, which could lead to overheating and fire. Moreover, it is important to ensure that all electrical connections are properly made and that all electrical components are in good working order. Loose or corroded connections can create resistance, which can lead to overheating and fire. Regularly inspect the electrical system for any signs of damage or wear, and have any necessary repairs made by a qualified electrician. Furthermore, ground fault circuit interrupters, or GFCIs, are important safety devices that can help to prevent electrical shocks. GFCIs are designed to detect ground faults which occur when electricity flows through an unintended path, such as through a person's body. When a ground fault is detected, the GFCI will quickly trip, cutting off the flow of electricity and preventing a potentially fatal shock. The NEC requires GFCIs to be installed in certain locations, such as bathrooms, kitchens, and outdoor areas. Consider installing GFCIs in other areas as well to provide additional protection against electrical shocks. Furthermore, arc fault circuit interrupters, or AFSIs, are another type of safety device that can help to prevent electrical fires. AFSIs are designed to detect arc faults, which occur when electricity jumps between two conductors, creating a spark or arc. These arcs can generate a tremendous amount of heat, which can ignite nearby combustible materials and start a fire. The NEC requires AFSIs to be installed in certain locations, such as bedrooms and living rooms. These locations are considered to be at higher risk of arc faults due to the presence of flammable materials such as bedding, furniture, and curtains. Also, consider installing AFSIs in other areas of the home to provide additional protection against electrical fires. In summary, providing a 90 amp feed ensures that the electrical system can handle the maximum potential load without exceeding the capacity of the circuit breaker. This prevents the circuit breaker from tripping unnecessarily and ensures that the heat strips and heat pump can operate reliably when needed. The NEC mandates the electrical system to be capable of handling the combined load of all connected devices, even if they are not expected to operate simultaneously.